Alright, good morning, good afternoon, good evening class. This is Mr. Arocena, and on today's video we're going to talk about the hydrolysis of salts. So in previous videos we talked about pH and pOH and the calculations involved in those. Today we're going to talk about how dissolving some salts will actually cause a rise in either one of these quantities. Some salts will do that, some salts will not. Alright, so first thing, what does hydrolysis mean? For those of you who've taken biology 12, I believe, you were probably introduced to a term called lysis, which was, I think, the term meaning to cut. Hydrolysis is basically this kind of the same way, only it's referring to how water, water can sort of separate the salts of an ion, or the ions of a salt, not the salts of the ions, the ions of a salt. So hydrolysis of a salt is what happens when you get water interacting with a positive ion and a negative ion of a salt. Now, as you know, ionic compounds are attracted by the opposite charges of their ions, and water, we always mention this in chemistry, is a polar molecule which has a slightly positive charge here and a slightly negative charge here. So what happens is that the water will actually attract the ions to itself. So the negative ions will actually attract to the slightly positive end of water, whereas the positive ions will slightly attract to the negative end of the water. Now, generally speaking, one molecule doesn't attract two ions to it. What will usually happen, and it's actually what actually happens, is that you'll have a second water molecule here, and these negatives will go to this water molecule, while these positives will go to this water molecule. So in effect, let me just erase one of these arrows. There we go. So in effect, the water molecules have split up. So this one, let's say this one had the positive ion attracted to it, like so. And then this one had the, oops, I should maybe draw them closer. So the negative ion would be attracted like that. So the water has effectively split or cut the ion into two separate pieces. Okay. Now, depending on what those ions are, those ions can actually further react to the water and can actually cause the water to create more hydronium or create more hydroxide. So in acid-base chemistry, this is what we refer to as the hydrolysis of a salt. And this will either make the solution acidic or it'll make the solution basic. And in some cases, it doesn't actually do anything to the solution and the solution remains neutral. So the first thing we need to do is identify what are the spectator ions. The spectator ions, like in every other instance we've mentioned spectator ions, they don't do anything. They just kind of sit there and watch. Here are some examples of spectator ions. These are, you'll probably notice what kind of substances these are. So the first here is sodium hydroxide, and the next one here is hydrochloric acid. So take a moment to think about what kind of substances these are. And we'll talk about these in a moment. So these are both strong. This is a strong base, and this is a strong acid. And as we know, strong acids and strong bases will create basic and acidic solutions. So here, this here does not react with water. Okay. And this one here does react with water because it will strip a hydrogen from the water and force the water molecule to become OH minus. Doesn't actually like change much because you still end up with a hydroxide, but that's kind of what the hydroxide ion does. It'll strip one of the hydrogens straight off of the water and become this. Over here, this is a strong acid. So this substance here is a spectator ion, again does not react with water, and this one will attach itself to water to become hydronium, like so. So strong acids and strong bases have this effect where the for strong base, the hydroxide end forces the solution to become basic, which kind of makes sense. And for the strong acid, the hydrogen forces the water to become hydronium, which again kind of makes sense as a strong acid. These two substances, the NaCl or the Na plus and the Cl minus, those two ions, they don't react with water. So they're kind of spectator ions, which kind of goes along with what we've known from the solubility unit, where these alkali ions tend to not be reactive with water because they don't tend to form anything, so they kind of just spectate. Chloride ions are a little different depending on the situation, but in terms of acid-base chemistry, chloride ions are spectators, meaning they don't react with water to create anything. So in conclusion then, spectator ions kind of fall into one of two categories. They are either ions of alkali metals, so these would be, alkali metals would be lithium, sodium, potassium, remember the order, rubidium, cesium, and francium. We generally don't deal with these last three though, because they're rare and hard to find. So anyway, so these are spectator ions. In terms of acid-base chemistry. The anions, spectator anions, end up being the anions of strong acids. So if you notice, like here's the perchloric ion, the iodine ion, bromine ion, chlorine ion, and nitrate ion. The only exception to this is the conjugate base of sulfuric acid. So HSO4 minus is not a spectator, because this is an amphiprotic substance and can actually act as an acid or a base. Okay. So yeah, so this is kind of like our quick and handy reference. If I'm talking about spectator cations in terms of hydrolysis for acid-base chemistry, they are alkali metals. That part makes sense because alkali metals tend to always be spectators in every form of chemistry. And then the spectator anions are the anions of the strong acids. Or another way to think about this is the conjugate base of strong acids. I'll put an or. Conjugate base of strong acids. With one exception, and that being HSO4 minus. Okay, so it's generally a good idea to try and memorize these spectator ions. It'll help just speed up some of the things we'll talk about later. All right, so how can we put this into practice? Well, here's a few examples that we can do to sort of get the idea of when you dissolve a salt, sometimes the ions react with water to do stuff. All right, so here's a substance. This is potassium chloride, very similar to sodium chloride. Will this resulting solution be acidic, basic, or neutral? So the first thing you want to do is to dissolve it. Write out a dissolving equation. So not calcium, what am I talking about? It's like potassium, K is potassium. Potassium chloride will dissolve into potassium ions and chloride ions like this. Now 2, we'll identify any spectators. Identify spectators. In this case, both K plus and Cl minus are spectators. Okay, K plus being an alkali metal, Cl minus being the conjugate base of a strong acid. So a solution will be neutral because neither of them will react. Neither of them will react with water, so the solution remains neutral, or whatever pH it was originally. Solution is neutral or unchanged in pH. Okay, so that's kind of our steps. We write out our dissolving equation, identify our spectator ions, and then the solution is neutral because both of them are spectators. All right, next example. This one's going to be a little bit more difficult because now we no longer have a simple salt like potassium chloride. But the steps kind of remain the same. So NH4NO3 will dissolve this. This will turn into NH4 plus and NO3 minus. Step 2, identify spectators. and spectators. Hopefully you've identified one of them as I finish writing this down. That one is going to be NO3 minus because this is the conjugate base of HNO3. So I'll write that down because conjugate base of HNO3. So what does that mean then for NH4? So I'll put down 2B. Okay. Find NH4 plus on table of weak acids and bases. So what I mean by that is I'll bring up the Ka table that we've been working with for the last couple of lessons. Alright, so here we go. So here's our relative strengths of Bronsted-Lowry acids and bases. So we're going to look for NH4 plus. We're going to find NH4 plus. NH4 plus is actually pretty far down on the list. There it is. There's NH4 plus. So if you look at NH4 plus, let's see if I can zoom it in a little bit to go. There's the ammonium ion. Okay, so there's NH4 plus. And what that means is that, okay, if NH4 plus is here, it's going to act as a weak acid, and then it'll move in this direction. So it'll move, whoops. It'll move, because it's on the acid side of this table. It's going to act as an acid and create H plus ions. So what we can say then is that because NH4 plus is a weak acid, then the NH4 plus ion will react with water to create hydronium. So NH4 plus, this is the reaction that NH4 undergoes. NH4 plus water will react to create hydronium and NH3. Okay, so then now we can say, okay, well, this solution is creating hydronium, so therefore the solution is going to be basic. No, sorry, not basic. Solution is going to be acidic. Solution is acidic. All right, there we go. So slightly different than the previous example. In the previous example, we had two spectator ions, so solution way neutral. In this example, only one of them was a spectator ion, and the other one ended up being a weak acid, so the solution ended up becoming acidic in nature. All right, on to the next example. Here we've got lithium hydrogen carbonate, or this is lithium bicarbonate. Very similar to sodium bicarbonate, which is what you would know as baking powder or baking soda. Actually, baking soda, not baking powder. So steps are the same. We take our substance and we dissolve it. Now these types of substances, some people might get the idea that it'll dissolve into 3 separate ions, but it does not. This is a polyatomic group. It's not a common one you'd normally see in, say, like Science 9 or Science 10, but it is one. So this would end up being Li plus and then HCO3 minus. So 2, the spectator ions. We know that lithium is a spectator. And then HCO3 minus is not a spectator. So 3, we now find where's HCO3 on the chart. Now this one's actually interesting because if you look for HCO3 on the chart, HCO3 minus, you should find it in 2 different places. Okay. Take a moment to go look for it and then we'll continue on. All right, so HCO3 you should find in 2 different locations on this chart. The first is up here. So up here, there's the HCO3 minus, and in the second place you find it is here. HCO3 minus is down here. Now you got to ask yourself, which one is more likely to occur? Is it more likely to act as an acid, or is it more likely to act as a base? Okay, and for this, we're going to do a little bit of math for this. All right, so what we're going to do is we're going to compare the Ka of HCO3 as a base, and we're going to compare, or sorry, the Ka of HCO3 as an acid, and we're going to compare it to the Kb of HCO3 as a base. So HCO3 minus is amphiprotic. So we have to compare we compare its Ka and Kb. And essentially it boils down to which one is bigger. If Ka is bigger than Kb, then the acidic form of HCO3- is more prominent. If Kb is larger than Ka, then the base form of HCO3- is more prominent. So for the Ka, that's easy, because that's just right in the table. So if we go back to here, here's the Ka. So here is HCO3- as an acid, so its Ka is this value here, 5.6 times 10 to the negative 11. 5.6 times 10 to the negative 11. Now its Kb, and this is important, if you remember back a few videos ago, I mentioned that if you want to find the Kb of a substance, you have to look at the chart at when is it acting as a base and calculate it from there. So we know that the base form of HCO3- is here. So we're going to calculate its Kb using this number here. Because if you remember, Kb is equal to Kw divided by Ka. In this case, Kw we'll assume is 1.0 times 10 to the negative 14. And the Ka, we're going to use this number here, because this is the equation where HCO3- is acting as a base, so we need to use this Ka when calculating its Kb. So 4.3 times 10 to the negative 7. All right, so this is going to be approximately, let's see, let's pull out the calculator. I'm going to do this like so. So this will be 0.23. So 1 divided by 4.3, 0.23. And I'll use exponent rules to solve this. Minus 14 minus negative 7. So it's really plus 7. So this will be negative 7. Cleaning this up a little bit, we'll get 0. Wait, no, not 0. 2.3 times 10 to the negative 8. There we go. All right, so there's the Kb. Its Kb is this. Its Ka is this. Kb looks to be greater than Ka. So the solution will be basic. Therefore, solution is basic. There you go. And the reason the solution is basic is because the equilibrium between the base form and acid form of HCO3- favors the base form, simply because the Kb is bigger. Okay. All right. Last example. I think it's the last example. Here we have a substance. This is ammonium fluoride. This is not the last example, it's the second to last example. NH4F is dissolved in water. Is the resulting solution acidic, basic, or neutral? So, start off. You guys are probably familiar with this after going through the last two examples. So NH4F will dissolve into NH4+, and then F-, like so. Now here, there are no spectators. We know from the first example that NH4- is not a I spelled spectator wrong. So we know that from the first example, NH4+ is not a spectator, and F- is not the conjugate base of a strong acid, so we know it's not. So now we look and see, where do these fall? Well, we know NH4+ is going to have an acid form, so NH4+ will go towards hydronium and NH3 from the first example. F-, however, well, you can probably guess what F- is going to do when in the presence of water, because there's no hydrogens for F- to give, so the only option is for the fluoride to gain a hydrogen and create hydroxides. So we have one substance creating an acidic solution in the NH4, so this is an acid reaction, and we have another substance creating a base reaction. So what will the resulting solution be? Now a lot of you might think, well, the solution is obviously going to be neutral because we have an acid reaction and a base reaction. That might be your first instinct. If you stop and think about it for a moment, though, you might realize, wait a minute, that might not be right. Because when we look at our table, remember what all these Ka values are? The Ka's determine kind of how much hydronium is created. So if this Ka value here is very large, then it'll create a lot of hydronium. If it's very small, it won't create that much. So maybe the solution might not be acidic if the base form is actually stronger. So if you remember from our previous example, here's NH4. NH4 actually has a pretty low Ka of 5.6 times 10 to the negative 10. So let's write that down. So NH4 plus Ka, 5.6 times 10 to the negative 10. 10 or 11? 10, yeah. So this Ka is kind of small. Now F minus is not an acid, so it'll have a Kb of some variety. And much like the previous example, we just have to decide, or have to compare, which one is bigger. If the Kb is bigger than the Ka, then the solution will be basic. If the Ka is bigger than the Kb, the solution will be acidic. And basically it just means that which equilibrium is more prominent. If Ka is larger, then this equilibrium is more prominent. If Kb is larger, then this equilibrium is more prominent, and I will decide whether the solution becomes acidic or basic. Now, how do I calculate the Kb of F minus? In the same way we did the Kb of the HCO3 minus from the previous example. We'll use the fact that Kb is equal to Kw over Ka. Kw 1.0 times 10 to the negative 14. And F minus will have a Ka based on its conjugate acid, which is HF, which is up here. There's HF. So it has a Kb of 3.5, or Ka, sorry, 3.5 times 10 to the negative 4. So 3.5 times 10 to the negative 4. Doing the calculation, so 1 divided by 3.5, this is about 0.29. 0.29 times 10, this will be minus 14 minus 4, so minus 10. So this is about 2.9 times 10 to the negative 11. All right, so now we decide which one is bigger. Well, here the Ka of NH4 plus is bigger than the Kb of F minus, therefore the solution is going to be acidic. Not very acidic though, because the numbers aren't like ridiculously large difference. Here we have 5.6 to the negative 10, and here we have 2.9 to the negative 11. They're not really that much of a difference of each other. So the solution is going to, but the solution will still be acidic because Ka is still larger than Kb. All right, last example. Here we have, this is hexaquachromium, I think. Yeah, it's a chromium ion with 6 water. So it's a hexaquachromium chloride. Is the resulting solution basic or neutral? All right. So this particular ion is very not common. This will dissolve into the following. You have your chromium, hexaquachromium, and then chloride. Okay, so we just have to recognize that this whole thing is its own ion. It's kind of confusing because I think it's the first time you've ever seen a polyaqua metal ion, but they exist. And this would be a 3+. So then we just gotta decide, okay, are there any spectators? There is chlorine. Chlorine is a spectator. Chlorine minus is spectator. Spectator. And then we look for this substance, the hexaquachromium. I think, oh, fortunately there it is, hexaquachromium. So there it is. It is an acid. So basically it comes down to, yes, is a weak acid. Don't even need to compare anything here because again, chlorine is a spectator. So therefore solution is basic. All right, so there you go. So depending on what kind of salt you have, if you dissolve it in water, you can actually cause the solution to become acidic or basic. Okay. Thankfully, most of the salts we use tend to not do that, but there are some salts that will increase or decrease the pH value of your solution. If any of you have a pool, this kind of becomes relevant because a lot of the stuff you dissolve in your pool to balance the pH or change the pH are basically salts that have this property where dissolving them changes the pH. Okay. Oh, also fish tanks. Fish tanks have a lot of stuff do that too. All right, so to recap today's video. If you're trying to figure out whether a salt will create a basic or acidic solution, the first step is to break the salt into ions. Identify and ignore spectator ions as defined earlier in this lesson. Because again, like in every other time we've talked about spectator ions, they do not react with water or anything for that matter. And then whatever ions are not spectators, we just determine how each of the remaining ions will act in water. And generally this boils down into comparing Ka and Kb, right? So you decide which one is an acid, which one is a base, calculate Kb if necessary, and then decide whether, or I guess compare Ka and Kb and determine which one is bigger. Solution will become acidic if Ka is bigger than Kb, and solution is basic if Ka is smaller than Kb. There you go. All right, so this brings us halfway through this unit. The assignment then for this is as follows. If anyone has any questions about it, you guys know how to contact me.